All right, and we're back. All right, today's title, Graphing Quadratic Functions. The little code in the book is 2.1.1. All right. So yesterday we kind of had some examples of what these paths of an object being thrown, they go in a parabola. Parabolas, remember, can be facing up or facing down. And basically, today we're going to look at the standard form of the equation for a parabola. These are called quadratics. We know something's a quadratic when it has an exponent of 2. That's how we know it's a quad. Okay. If it had an exponent of 3, it'd be a cubic function. Cube. Okay. But here we're talking about quadratics, so it has this x squared in my first term. In descending order, I know that that is the right order, x squared. Okay. So there's two different forms we're going to learn for this week. We're starting with standard form, and this is really the most helpful. A little bit further on in the year, we're going to do quadratic equations, and this is where we're going to start as well. So if you can really grasp this today, all the information that we need to grasp is going to be pulled out of this equation. Okay, so this is the one that's really important. Remember that this is function notation. F of x is kind of just a way, think of it this way, it's a way to remember what we're plugging in for x. It's just a way to remind us, what are we plugging in for x? There's no difference than if I wrote this as y is equal to ax squared plus bx plus c. It's the same thing. The y value and f of x in this function notation have the same purpose. But think of function notation, like I mentioned, as a way to remember what we're plugging in for x. So if I was plugging in 2, I would go into this equation, I would say f of 2. I put a 2 here for the x, and I put a 2 anywhere else I saw that x. Just tells you what to plug in. Okay. So the first step every single time when you have a quadratic like this in standard form is to take that equation and identify your A, your B, and your C. They're going to be in the same place every single time. We know that from this equation, our A value is the coefficient. It's the number in front of the x squared term.
Bless you.
It's the number in front of the x squared term. So if this was 3x squared, my A value would be 3. My A value doesn't include any of the variables. It's just that coefficient in front of that term. So my B value is always found as the coefficient in front of the x. My C value is always left over, and it's always a whole number. It's a way to remember that the C is just a constant. It's a number that's always going to be the same no matter what we plug in. So all we have to do is identify A, B, and C, and then all the other steps will just be plugging those in and kind of solving from there. So if I look at this equation right here, this is x squared. If I look at this equation right here, what is my A value? What is the value of A? Yeah, Daniel? 3. I look to the x squared because that's the term that's connected to my A coefficient here. And I know that 3 is my A value. Okay. How easy was that to identify? Pretty easy, right? If we're looking for A, B, and C, we always find them in the exact same place every time. So what's my B value for this function?
2x.
2, great. So that's 2, and it's positive 2. What's my C value?
1. Negative 1.
Negative 1. Remember that the value also always includes if it's positive or negative, because that would make a huge difference. So for the next one here, this function, I want you to go ahead and on your own just identify A, B, and C. You can underline it, you can circle it. It's whatever you like. So you might just go in and circle them and then identify, okay, this is my A, my B, my C. Really quick, really straightforward. All we're doing is identifying A, B, and C. Let me get rid of these circles. I see some weird confused faces from it. So you can underline it just like I did right there. Okay, how about 4 more seconds? Ding. All right. So what is my A value? Let's just call it out.
-5.
-5. Hey, what's my B value?
-3.
B. See?
10.
10. Okay. On a scale from 1 to 10, 1 being the easiest, how easy is it to identify A, B, and C?
10.
Don't even need it.
One's the easiest.
Don't even need
And
to
it's
lift
hard.
a finger. It's not even a question. Moot point. All right. So we identify A, B, and C. We feel pretty confident with that. We have to do that every time. And then we're going to use our A, B, and C values to find everything else we need to graph. Okay? So this is a real methodical approach. I hope that you can still connect it to what we did yesterday as far as how the object actually flew, because there's a lot of connections you can make with that. All right. First thing we're going to do every single time is look at this step 2. Does the graph open up or open down? Does it open up or does it open down? Remember, we can have some quadratics that open up. We can have some quadratics that open down. We can figure that out just from looking at the A value. The A value. If A is positive, if it's positive, it's a happy face, it opens up. If A is positive, it's a happy face, it opens up. If it opens up, then I know that this vertex, this very bottom point, has to be the minimum. Does that make sense? We wouldn't have a maximum in this case because the function goes down, it opens up, so it's caving down here. So we're only going to have a minimum for this one. Our maximums are going to kind of go on forever, they keep going forever, but this is what we can identify as a finite point. It's the minimum. So when A is positive, it's a minimum. When A is negative, it faces down. It faces down, sad face. A is negative, opens down. And then in that case, we have a maximum. At the very top of the roller coaster, we have a maximum, not a minimum. When we threw the tennis ball or the ping pong ball, we had a maximum. So that's just, I hope that's a little intuitive. When we have a dip that's going down, opening up, we end up with the minimum on the bottom. If it's face down, we end up with a maximum at the top. Those are just our two extrema, the extreme finite point, our extrema that we talked about in the warm-up. So looking at these two functions that we just identified A, B, and C for, does the first function here open up or open down? What's my A value?
Positive.
Positive 3. When A is positive,
It's up.
it's going to open up. How about for the second function here? A is
Negative.
negative, then it opens
Down.
down. Everybody agree with those two? So 1, we know how to identify A, B, and C. 2, we take our A value, we look to see if it's positive or negative, that tells me if it's going up or down, so we've gotten a little bit more information. We're still moving along with this. Great. All right. Number 3 is the hardest part, so I'd like to actually skip number 3 for a second and go to one nice and easy thing here. Step 4, if we need to find the y-intercept, the kind of more complete way to look at it is we need to plug in 0 for x to find what the y-intercept is. Because when x is 0, right, as x comes down, so this is negative 8, negative 9, as x gets closer to the origin, here's like negative 10, negative 5, negative 3, negative 2, negative 1. Let's start that over. These are positives. We got positive 20, positive 10, positive 5, positive 3, positive 3, positive 2, positive 1, 0. So when x is 0, I know I'm on my y-axis. I know I'm on my y-axis. So if you wanted to find where any function crosses the y-axis, you can plug in 0 for x. And that tells you at x is equal to 0, that's going to give you the place to look really to see where does maybe the function cross. So here x is 5, 4, 3, 2, 1. I know that's where it's going to cross my y-axis. So what's nice about this with quadratics, if we plug in 0 here for these two x's, what's going to happen to these two terms?
They become
0, 0. What's left over? That constant. So I know my shortcut here is the y-intercept is going to be equal to my c value. So let's recap. We found a, b, and c. We found a, b, and c from the standard form. We look to see if it opens up or down. If a is positive, it opens up. A is negative, it opens down. I know I can also grab from this information that whatever my value for c is, that's where it crosses my y-intercept. So far, so good? All right. We only have one other piece, and this is a two-part. It's two parts to this, but I think we're going to be able to do this. I think we're going to be able to do it, no problem. I'm going to do it on this side, actually. Can I see here? Not quite. Let's move this. All right. Next, we need to find the vertex. We know that vertex is on my axis of symmetry. It's the very top or the very bottom, where the left and the right side are symmetric to each other. You can even forget that for a moment. You can just focus on this. Once you get the vertex, that'll become really apparent. Find the vertex using A, B, and C. We're going to use this vertex formula to start out. And actually, this is also the formula for the axis of symmetry, believe it or not. So we look here, x is equal to negative b over 2a. I know what my b value is. I know what my a value is. So I can go in there and plug that in pretty quick. So how about we use an example problem over here and kind of work out what we've done. So let's use... Let's do this one. F of x is equal to 2x squared plus 4x plus 3. We're going to do all our steps and then find the vertex because that's the hardest part. So let's put it here. All right, we're going to be moving things around. So looking at this problem here, let's go ahead and identify my A, B, and C. Just call them out. A is 2, B
4,
positive, good. C
3,
positive 3. Pretty straightforward. Let's look for the next step. Does it open up or down? Is A positive?
yes,
A is positive, so I know it opens
up,
up. I know it opens up. Okay. How about number 4 here? Find the y-intercept. What's my y-intercept?
3,
3. Y-intercept. Do you see how easy it was to find those 3 things? We can do that over and over pretty quick. The vertex is what takes time. First step is, let's go ahead and take and find our x value for the vertex, negative b over 2a. I suggest putting that b in the parentheses.
4,
And let's plug in what we have. X is equal to
4,
negative 4 over 2 times 2. I took my b value, I figured that out, I put it in. I took my a value, I substitute that in, and now we just need to solve this out. X is equal to negative 4 over 4. X is equal to negative 1. Okay. I have half of the problem done here. Remember that your vertex has an x and a y component. So I know that x is negative 1. Anytime you have one part of a coordinate that comes from a function, you can plug that coordinate into the function to find what the other part of the coordinate is. So I know my x, I need to know my y. So the step 2 of this part is plug in your found x value to find your y value. You're going to do that in the original equation. So I'm going to go ahead and take f of negative 1. Remember, a function just tells me what I'm plugging in for x. That's 2 times negative 1 squared plus 4 times negative 1 plus 3. All right, let's just evaluate this. F of negative 1. Negative 1 squared is 1 times 2. 2 Positive 4 times negative 1, negative 4 plus 3. So I know that f of negative 1 is 2 plus 3, 5 minus 4.
1.
So I found out my x value, I found out my y value. So I know that my vertex is at negative 1, positive 1. So we can go in here from all that information, graph this pretty directly. So let's look and see, what do we know? We know it opens up. We know that the y-intercept is at positive 3. Okay. We know our vertex is negative 1, positive 1. Now, Isaac, the vertex lies on the what?
Oh, the vertex